Hey everybody, this is Mr. Johnson, and we're going to be going over the PM2 notes. I'm going to be doing these a little differently. We'll see how it works. The notes are actually going to be filled out already. So when the key is up on the board, you can go ahead and copy it down, but you need to make sure that you're paying attention to my explanation so that you understand the context for how everything is laid out. This can be fairly confusing, but I'm going to try to make it as straightforward as possible. So just keep your ears sharp and make sure you're getting the numbers down and the explanations. So yesterday you should have played Deal or No Deal. Hopefully you kind of saw that there are a lot of different options that you can go with. I actually played myself and I kind of recorded some of my numbers here in the bottom of the front page of your notes. I ended up winning $202,000, which is not bad, but I settled for the deal. When I picked my original suitcase in the very first choice at the beginning, I didn't know what it was, and as I was working down, I had a couple of different options. One of those options that was left over was $750,000. And so gradually as this number went from 12,000 to 27, and then just higher and higher and higher, I started to get a little bit nervous, and so I settled here for $202,000. It turned out in the end, it just kept going until the very last suitcase because I had $750,000 in my suitcase. I was a little bit bummed though in the second round here. I lost my $1 million suitcase, so I'm still pretty happy because what can't you do with 200 grand? If you go ahead and flip with me to the second page here on our notes, we're going to get started with a definition. It's a very simple idea, but it's an important idea because everything hinges on it. So this first vocabulary idea is called the general multiplication rule, right there. So for any process involving multiple options or multiple steps, the total number of different ways that you can complete that process is found by multiplying all of those options out. We've actually done that already. So if you thought about the game of craps, how many different options are there for rolling two dice? Because one dice has 6 options and the second dice has 6 options, you take 6 times 6, and there are 36 total. Very important idea there. That is something we've used, we just haven't had a name for it yet. It's called the general multiplication rule. So let's go ahead and let's look at question number 1. Suppose that you're playing a new board game that bases its moves and strategies from tossing a fair coin, an 8-sided die, and a regular 6-sided die. And this is all at once. So you have 3 things that you're tossing, and maybe you get to choose or you get to do different things like that. How many different possible moves are there? So if we think about a fair coin has 2 options. Obviously an 8-sided die has 8 options. And then a 6-sided die has 6 options. So you just take those and you multiply them up. 2 times 8 times 6 is 96 total options. And again, that's if you're throwing them all at the same time. So for that question, if you just get 2 times 8 times 6 and you have 96 total options, that's great for your notes. Just so long as you can remember and you know what you're doing. Question number 2, kind of similar. A bank requires its customers to choose a 4-character personal identification code to access their accounts on its ATM machines. The bank requires that 3 of the characters be a digit, so that could be from 0 to 9, while the other character must be a letter. How many different codes are there? How many different codes are possible? Well, it doesn't really matter. How I've done my work, I have 10 times 10 times 10, which those are the number of options for the digits. Think about 0 through 9, right there. If you count those up, there are actually 10 numbers, 10 digits. So 10 different digits, 10 different digits, 10 different digits, and the last one here, the remaining piece, is 26. Why is it 26? Well, that's how many options there are in the alphabet, 26 letters. So it didn't have to go 10 times 10 times 10 times 26. If I wanted the 26 in front or in the middle, I'm still going to get the same answer. That answer is 26,000 different ID codes. So that's actually not bad. You don't want a low number here for different ID codes because that means you're fairly limited. You can't have a lot of people using your ATMs. Question number 3. Suppose restaurants offer a special menu to large groups that include choices of an appetizer, main course, and a dessert. Suppose a restaurant's menu gives 3 choices for an appetizer, 5 for their entrees, and 2 dessert options. How many different meal selections are possible? Well, this is pretty easy. If we take the number of desserts that are available, 3, times the number of entrees that are available, 5, times the number of desserts, 3 times 5 times 2 is 30 different meal combinations. So you could go there every single day of the month and get something new, a different combination of foods. Hopefully those first 3 questions make a little bit of sense to you, and we're going to try one that's a little trickier, but still the same general rule for its math. Question number 4. As you are aware, every week Mr. Chipman reads the morning announcements, and I'm always encouraged by his message and impressed by his eloquent recitation of the Pledge of Allegiance. I think it's great. As I thought about kind of the style and his pace for the pledge, I began wondering how many different unique ways he could speak the Pledge of Allegiance each week. So you could speak a word with regular intonation, so just kind of monotone or flat. You can emphasize it, put a little oomph behind it, or you can pause after the word for effect. So how many weeks could Mr. Chipman read the announcements and never recite the pledge in the same way twice? Now, keep in mind, the Pledge of Allegiance has 31 words. Each word could be said in 3 different ways. So I've kind of drawn a little diagram to help us think about this. So we have regular, which is just regular font right here on top. And then I have italics, which would be emphasis behind his words. So I pledge allegiance. And then there's ... down here on the bottom, and that's pausing for effect. So out of those 3 different options, here in this first word, I have 3 choices. In my second word, I also have 3 choices. And I've kind of drawn different arrows saying that I pledge. It could go in different ways. Regular, I pledge. Then regular to italic, or maybe italic to pausing. So there are lots of different combinations of arrows. 3 times 3, there are actually 9 combinations. If I go ahead and go to just the third word out of the Pledge of Allegiance, I now have 3 times 3 times 3 different options. Because maybe I go down here, but then I go back to the original. Maybe I go over and then I go to the bottom. 3 times 3 times 3 is 27 different ways. And this is just for the first 3 words. What happens if we go out for the full 31 words? Well, if we take 3 times 3 times 3 times 3 all the way out, I pledge allegiance, and then you end with for all, you get 31 words, which is 3 to the 31st power. That's a fairly big number. If you look over here, I wrote out the actual answer that you'd get, 617, 673, 396, 283, 947. Now that's the total weeks that he could say it in a different way. I kind of wanted to get a grasp of how big of a number that was, or how long, so I converted it into years, and that's about 11 trillion years. So, yeah, that's a long time. So now when Mr. Chipman comes on the announcements, you should be excited for a new, rousing rendition of the Pledge of Allegiance. We'll have to keep track of how many different ways he can say it. So there's our first rule, the general multiplication rule. That's pretty easy. We start to build on this with our next idea. Our next idea is called a factorial. A factorial is the product of the number, and usually we use n to represent a number, by 1 less than n, then multiply by 1 less than that value, then multiply by 1 less than that value, all the way down until you get to 1. So in symbol notation, we usually write n factorial using an exclamation point, n exclamation point. All right, and somebody literally just made this up. They thought it was kind of useful, so they called it a factorial, and they said these are the rules that a factorial will follow. It's kind of neat that somebody was inventing math like this. So it just means this, n the original times 1 less times 2 less than that original number times 3 less until you get all the way down to 3 times 2 times 1. You will always finish multiplying by 1. One thing that you have to kind of note, and mathematicians argued about this when they were creating factorials, what is 0 factorial? There are a lot of good explanations behind this, which I don't want to tell you, at least not yet, but 0 factorial is equal to 1. So if you ever see that, just know 0 exclamation point is the same thing as 1. So a couple of examples to get the hang of a factorial, a new idea for us. Find 6 factorial. Well, that means we start off with 6 and we multiply by 1 less, which would be 5, then 4, then 3, then 2, and then 1. So we always end with 1. 6 times 5 times 4 times 3 times 2 times 1 is 720. 10 factorial. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 3,628,800. And then 3 factorial at the end. 3 times 2 times 1. That's just 6. Believe it or not, your calculators can actually do factorials for you. Because I suspect some of you with your rinky-dink phone calculators are just typing away, and what happens if you hit one wrong button? It can really ruin your whole answer. So if you go ahead and go to your calculator and hit math, which is right down here, you have math, numbers, complex, I believe, and then probability. Arrow over to probability, and you can see the fourth option down is the exclamation point. If we hit enter, we need a number in here to take that factorial of. So let's go ahead and let's do 10 factorial. Let's see if I did that problem correctly. So 10 factorial, hit enter, 3,628,800. So my answer was correct for that one. Now factorials deal with problems where there are n options, 10 options, 6 options, 3 options, whatever it might be. And you have to use all of those options. The idea is that your options become more and more limited as you progress along. You can't use things over again. So if you've set something in stone in the past, it stays there, and then you have one less option as you go to the next spot, and then one less because that is now in stone. So that's going to help us with question number 5. Suppose that an assembly operation in a manufacturing plant involves 4 steps, which can be performed in any sequence. It doesn't matter. If the manufacturer wishes to compare the assembly times for each of those sequences, how many different sequences will be involved in the experiment? So for this first position, I could choose any of the 4 total options. But once I put 1 in place right here, I am not going to have 4 options anymore. In fact, in this next position, I only have 3. After I put that in, I'm only going to have 2 left, and then with my final space, there's only 1 option. Okay, I've used my other 3. There's only 1 left. So 4 times 3 times 2 times 1, that is the idea of 4 factorial. We could put this in our calculator if we wanted. 4 factorial is 24. 24 different assembly options. Let's go ahead and let's move on to the third page with question number 6. If you've ever been to Ikea, which if you don't know, Ikea is a Swedish-based company. It designs and sells furniture that you have to assemble yourself, and they have kitchen appliances and home accessories and things like that. But they have unusual names for their products because they're Swedish. Recently, I visited an Ikea in Schaumburg, Illinois, and that was for the first time. And I was kind of wondering as I was walking around the store how they pick the names for their products. Maybe they just take a name and they scramble around the letters and they come up with a new name. So I was taking some pictures of these unusual names, and I thought, what if we had maybe this product, and it has the letter CHOSIGT, no repeating letters, which is kind of important. How many unique names could be assigned to future products if they just kept rearranging the order every single time, scrambling it up? So you don't want to get a repeat of this, you want different ones. So we can find this answer by taking 7, which would be all the letters, and you can use any of them for that first position. But after you use one of those letters, you are limited to 6. Okay, that first one is set in stone. After you set those first 2 letters in stone, now you only have 5 left over, then 4, then 3, then 2, and then 1. This is just 7 factorial, which you could find in your calculator. If you do 7 factorial, that is 5,040 different unique names, just from that one set of letters. Imagine what you could do if you maybe made the word longer, or maybe you switched out a couple of letters. The possibilities are almost endless. It is pretty crazy. So it was really interesting to kind of see what weird things they were selling. This is a cheese grater. What a great price, $5 for a cheese grater. Dishwasher safe, all that good stuff. And it's got a good bit of math with it. Who knew Ikea was so cool? What about question number 7? A teacher has 15 seats in her classroom and 15 students in a particular class. How many different seating arrangements are possible? So we're just going to go ahead. In the first seat, we could put any of those 15 students. But after they're sitting down, the next seat, I only have 14 to choose from. I'm not going to take the first person and then move them to the next seat. That'd be silly. So the third seat, you can only sit 13 different people. And then it keeps going until you get down to that last person who's standing at the front, really awkward, hashtag Mr. Johnson. And then they'd sit in that last seat, probably in the corner because nobody likes them. So 15 factorial. If we put that in our calculator, 15 factorial and hit enter, we get E. Now E means scientific notation. A lot of times that happens because our calculator screens are too small to fit the entire number. I was fortunate enough, I was doing this on my computer, I could get the whole thing. So when we write it out, it is going to be in the trillions. It's a 1 followed by 307, 674, 368000. That's all the different seating charts that they could come up with. So you could have a new seating chart every single day, and it would never be quite the same, and you could do that for years and years and years. Let's go ahead and let's finish up factorials with question number 8. Think back to the game that we played to open the Notes Deal or No Deal. If we played the game all the way through to the very last box, which was 26 cases total, how many different unique games could there be? We are not keeping in mind that the values would switch from game to game, the amount of money. I just want to know the different ways to choose your boxes. So that would be 26 factorial. Putting 26 factorial in your calculator, you are going to get scientific notation. So I did it on my computer. I don't even know how big this number is. It is gigantic. 403, 291, 461, 126, 605, 635, 584, 000, 000. That is a mind-blowingly big number. It's gigantic. And that's the different games that you could have in terms of choosing boxes. Hopefully you understand factorials a little bit better. They are not hard, and it's nice that our calculators can do them. And again, this is for having different choices as you move through a progression. So this kind of brings me to a question. Factorials are great if we want to use all the possible options, but what if we wanted to stop early? What if I didn't want to choose all 26 boxes up here in the deal or no deal problem, and I'm only going to 20 boxes? Well, in order to figure out this idea and how to make it work mathematically, let's start with 2 small examples. What if I'm dealing with 6 factorial, but I want to stop when I get to 3 instead of 1? Well, normally 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. It's right here. But I need to almost snip off that last piece. So notice how I put that diagonal slash through there. How can I get a 2 times 1 canceled out? Well, I can cancel them out actually by dividing. So if you look over here, I put 6 factorial in the top of a fraction, and then I put the numbers that I needed to cancel out in the bottom as well. That way 2's will cancel, 1's will cancel, and I'm left with just this first piece. 6 times 5 times 4 times 3. So the top, if we were to rewrite that idea, that's 6 factorial. The numbers that I needed to cut out, those are on the bottom, 2 factorial. So would this work for another problem? So what if I'm dealing with 10 factorial and I wanted to stop at 4 instead of 1? So I wanted to go 10 all the way down to 4. On top, 10 factorial right there. But then crossing out 3 and 2 and 1 means I need to have 3 factorial on the bottom. This kind of moves me towards some more complex math, a little bit more powerful math. And that is the next definition. The idea of permutations is incredibly important for probability. Permutations are distinct arrangements of individuals where the order matters. That is extremely important. The order matters. I put it in bold. You might want to underline it or highlight it. If I switch the order of just 2 individuals, I create a new arrangement or a new list that's unique from the first one. So in symbol notation, there's a special way to write permutations. It goes like this: small n, big P, small k. Sometimes we use the letter R there, so it could be NPR. It doesn't matter. K and R, they would represent the same thing. So what does N mean? N represents the total number of things you are selecting from. So if I have 100 people, this would be a 100 in the front. Now I don't have to choose all 100. What if I wanted to stop early and I'm only going to choose 30 people? Well, that's where this next number comes in. So out of 100, I am choosing 30. K, or R, represents how many you are selecting from those n things. So it's how many people I'm choosing. So from 100, I am choosing 30. That's what you should think every single time. The P just stands for permutation, and what you should think there is that the order matters. The order really matters. Now, mathematically, there is a formula that goes with this. It is NPK equals n factorial divided by n minus k factorial. So factorials are showing up in this formula. Let's look at question 9 to see how that would work here. This is a question that probably has a little bit of relevance to you in your lives, because most of you have the opportunity to drive, and if you're driving, you have to have a license plate on your car. Illinois has very strict regulations for license plates. If you're ordering a vanity plate, which is just the regular license plate, you don't get to choose those things. There can't be more than 3 numbers or 1 to 7 letters. You don't have to get one of those, though. Those are the regular ones. You don't pay a lot. You could have the option to personalize your license plates. Now, you're allowed to have a little bit more freedom here, but you have to pay more money to do that. You can intermingle both letters and numbers. If you're going to personalize a license plate for yourself, how many unique license plate combinations could you choose from? So let's think about this. Letters and numbers. I know that there are 26 letters, and the digits that I could choose from, 0 through 9, there are 10 total. So 10 digits, 26 letters, that's a total of 36 options. So 36 options here for each position. Now we're only choosing 7 places worth, so we're doing this 7 times. So because there are 36 total options, and I'm choosing 7 of those options to get stuck on my license plate, and because the order really matters here, that's what my little note over here stands for. If you had ABC 1, 2, 3, 4, that is different from having ACB 1, 2, 3, 4. Even though they have the same letters overall, the order matters. Switching 2 positions creates a new license plate. Because that order matters, we're using a permutation. So going back to my formula right up here, I have n factorial, which is the first number, so 36 factorial, divided by n minus k, so 36 minus 7. Just kind of doing some of the simpler math. 36 factorial stays on top. 36 minus 7 is 29 factorial. So behind the scenes, what's happening here is I'm having 36 times 35 times 34 times 33 times 32, all the way down until I get to times 1 at the end. But on the bottom, I have 29 times 28 times 27 times 26, and the 29s are going to cancel and follow that all the way down until there's nothing left. Even the 1s at the end cancel. So this is what's happening behind the scenes. You don't have to write that down, but it's good for you to understand that. You could, if you wanted, just put this in your calculator, which is usually what I do. 36 factorial, divide that by 29 factorial. Go ahead and enter. You're going to get scientific notation. That just means there are a lot of options so long as that E is a positive number. So if we move that over, that we'd have to move it 10 times. That's going to be 42,072,307,200 different license plate options. That's enough options for everybody on Earth to get several different license plates and have no repetitions. Hopefully the idea of permutations makes a little bit of sense to you, because there's something that's related to permutations that's a little bit different. Flip to the next page, and we're going to learn about combinations. If the order doesn't matter, and you can switch individuals around and it doesn't change anything in the grand scheme of things, that is the idea of a combination. Combinations are selections of individuals from some group where the order doesn't matter. Okay, again, that's in bold because it's important. Switching the order of 2 or more individuals doesn't make a difference. For this class, we are not going to allow repeat individuals to be a combination. So you can't have chocolate scoop of ice cream, chocolate scoop of ice cream, chocolate scoop of ice cream. That won't work for our combinations. That is actually a lot trickier to include those types rather than have like chocolate, vanilla, banana, okay, or banana, chocolate, vanilla. The order doesn't matter because you're getting the same 3 scoops. If you start to have chocolate, chocolate, vanilla versus chocolate, banana, vanilla, that is a lot harder to deal with. So the symbol notation for combinations, I'm sorry, I missed that there. That should say combinations, not permutations. It looks very similar. N, the number of things that you're selecting from, and then K, how many things you are actually selecting from that group, and then C standing for combinations where the order doesn't matter. You can switch things around. The math formula is also similar. Notice on top it has n factorial. Notice on the bottom it has n minus k factorial, but there's a little bit more on the bottom, and this helps out with the fact that you can switch the order and it's still the same answer. You are also dividing by k factorial. So 2 things on the bottom, 1 thing on the top. Let's try a question to see if we can put that formula into practice. Question 10. You're in your favorite fast food restaurant and would like to live life on the edge a little bit. So you order a large soft drink. Now you decide that a large drink just wasn't exciting enough. So you're going to mix some of the drinks together to make a mega awesome super drink. Now there are 14 different options, but you only want to put 4 types into your drink. I mean, let's not get too carried away here. How many different drink combinations are there? Now, does the order matter here? If you read my note down here at the bottom, which you don't have to copy it down, just understand it. The order doesn't matter because, let's say you put Mountain Dew and then Coke. That's the same result as putting Coke and then Mountain Dew. It's the same 2 sodas overall. There's no difference in the outcomes. They're both gross. So how many options do we have total? Well, we have 14. How many are we choosing from those 14? We're only going to be choosing 4. Okay, that's what the problem said right up here. So if I'm going to put these things into my little formula, n factorial goes on top, so that's 14 factorial. K factorial goes on the bottom, which is 4 factorial. And then I have n minus k factorial, 14 minus 4 factorial. If I do the simple math, 14 minus 4 is 10, so I'm kind of sitting right here at the moment. You could put that in your calculator. In fact, that's what I did. But what does that mean? If you write it all out, 14 times 13 times 12 times 10 times and all that stuff. I missed 11, I think. But if you go all the way down to 1, and then you go ahead and put 4 times 3 times 2 times 1, and then 10, 9, 8, 7, 8, all the way down to 1. Those numbers cancel out. 10 all the way down to 1, and you're just left with 14, 13, 12, 11 over 4, 3, 2, 1. That's not a hard problem if you understand how factorials work, but that's what's happening behind the scenes. So putting that in your calculator, 14 factorial divided by, and you need to be careful to group 4 and 10 together, 4 factorial times 10 factorial. Close your parentheses, go ahead and enter 1001. There are 1001 different drink combinations that you could have at that restaurant. Sounds like a pretty good deal to me. Question 11. During Super Bowl LII, which is 52, and this is the most recent Super Bowl where the Philadelphia Eagles beat the New England Patriots, Pringles ran a commercial touting the fact that you can mix and match different chip flavors to create your own recipes. Now, I had to look this up. There are 34 different flavors of Pringles in the United States. Let's say we wanted to make a triple layer Pringles creation. How many different unique combinations could there be? So out of the total, which was 34, we are only going to be choosing 3 of them. Remember, repetitions is not allowed. So we can't have ranch, ranch, ranch. Okay, they have to be different. So putting this in my formula, 34 factorial over 3 factorial over 34 minus 3, which is 31 factorial. Putting that in my calculator, make sure you group the bottom together down there so they don't escape. You get 5,984 different Pringles combinations or concoctions for being a triple layer creation. I was going to put the Pringles ad in here. I don't know if my video would get taken down for copyright infringement, so you'll just have to look that up on your own. Question 12 is actually a good thinking question. If you had the same problem with the same numbers for n and k, which of these would be larger? P for permutations or C for combinations? And why? Permutations are going to be larger because if you change the order of 2 items, such as like if you go 1, 2 to 2, 1, that's a new answer. Whereas for combinations, those are the same thing because both have a 2 and a 1. The order doesn't matter there. You can also see this back in their formulas. For combinations, you are dividing by a little bit more than permutations. Permutations don't have the k factorial piece. So if you're dividing by less, your answer will be more. That's why permutations are more. And question number 13, probably the last question that we're going to do here for this class. We'll finish up the notes tomorrow. 13 says, identify each scenario as permutation or combination. You don't need to solve them. The hardest thing that I find students struggling with is just which one is which. Permutations, the order matters. Combinations, who cares? It doesn't matter at all. You can switch them and you get the same result. So I want you guys to go ahead through all of the parts of 13. 13 goes all the way to the next page, and you need to go A through I. Give it your best shot at selecting if it's a permutation or a combination. We'll pause the video, and then I'll go through all those answers and explain them a little bit so you can understand why. So take a minute. Let's get your thoughts down. All right, so let's see what you have here for question 13. For A, suppose that 7 people enter a swim meet, assuming there are no ties, and how many ways could you have a gold, silver, and bronze medal be awarded? This is a permutation. The order matters. If I get first and you get second, we get different prizes, whereas if you got first and I got second, it would be switched around. Order matters. B, how many different committees of 3 people can be chosen to work on a special project from a group of 9 people? This is a combination. So I know it's 3 different people, but if you choose Tim, Bill, and Amy in that order, is it different from Amy, Bill, and Tim? It's the same committee. It's the same 3 people. So the order does not matter. C, a coach must choose how to line up his 5 starters from a team of 12 players. How many different ways can the coach choose the starters? So this one might be able to go in a couple of different ways, but they say it's a permutation. And I think this makes a little bit of sense. So if you're taking these individuals and you're lining them up to defend a certain person or to be in a certain position on the field, order matters. You don't want your point guard down under the basket, or you don't want your goalie in midfield. All right, the place that they are is important. So that means order matters, and it is a permutation. If you actually wanted to know how many different combinations that would be, how many different outcomes, it's 95,040 different unique ways that they could set it up. D, John bought a machine to make fresh juice. He has 5 different fruits: strawberries, oranges, apples, pineapples, and lemons. If he only uses 2 fruits, how many different juice drinks can John make? This is a combination. It doesn't matter what order he puts those 2 fruits in, he will get the same drink in the end. E, how many different 4-letter passwords can be created for software access if no letter can be used more than once? That is a permutation. The order matters. That's why if you're typing in your password and you just switch 2 things around, it will not let you into the website or whatever it is you're trying to use that password for. F, how many different ways can you elect a chairman and co-chairman of a committee if you have 10 people to choose from? This is a permutation because it's a chairman and a co-chairman. All right, those are 2 different levels. And because you have 2 different levels, like a president and a vice president, the order matters. Last one for this page, G. There are 25 people who work in an office together. 5 of these people are selected to go together to the same conference in Orlando, Florida. And how many ways can they choose this team of 5 people to go to the conference? This is a combination. It doesn't matter who gets selected first or who gets selected second. It's going to be the same team in the end. So it's a combination. On the next page with H, there are 25 people who work in an office together. Sounds familiar. 5 of these people are selected to attend 5 different conferences. The first person selected will go to a conference in Hawaii. The second will go to New York. The third will go to San Diego. The fourth will go to Atlanta. And the 5th will go to Nashville. How many different selections are possible? So in this problem, even though it's set up very similar to the previous problem, it is a permutation and not a combination because the order matters. If you're in first, you go to a different place than if you're in second. So switching the order switches where you go. It matters a lot. I, John couldn't recall the serial number on his expensive bicycle. He remembered that there were 6 different digits, none of them used more than once, but he couldn't remember what digits were used. So he decided to write down all the possible 6-digit numbers. How many different possibilities will he have to create? Just in case you are actually curious, it is 151,200 different combinations, so he might be there for a while. But this is a permutation because switching the order of 2 numbers changes it. It's a unique ID number. J, how many different 7-card hands can be chosen from a standard 52-card deck? This is a combination, okay? If you draw a 2 and then a 5 and then a 6 of diamonds in that order, and then if you think about maybe drawing them as a 6, a 5, and a 2, you still have the same overall hand. You just drew them in a different order. The order doesn't matter. It's the outcome of the hands that matter. K, 112 people bought raffle tickets to enter a random drawing for 3 prizes. How many ways can 3 names be drawn for first prize, second prize, and third prize? The order matters here because the first name will be for a different prize than the last name. Permutation. And the last part, a disc jockey, which that's where we get the phrase DJ from, has to choose 3 songs for the last few minutes of his evening show. If there are 9 songs that he feels are appropriate for that time slot, then how many ways can he choose and arrange them to play 3 of those 9 songs? So because the arranging matters, I mean, maybe you don't want to follow Taylor Swift with Metallica or something like that. This is a permutation. Hopefully you guys started to understand the difference between permutations and combinations a little bit better here by the end of that question. It's a good problem to think through, and it's very important for your homework and for your quizzes and for your tests. That's where we're going to head and wrap it up for today. I hope you guys learned a little bit about the multiplying rule, factorials, permutations, and combinations. Those are all really important and the big focus of probability models Target 2. Hope you guys have a great night. Bye.